the block has a weight N. The force required, let's call it T required, the force required for pushing this block, meaning to cause the motion or the sliding of the block, you know that this is equal to N times the coefficient of friction, which describes the interface between the block and the plate. So effectively what we're saying is that the coefficient of friction is the relationship between the force required to cause slippage and the weight of the block, which is the force that is normal to this interface. Now, another term for this force, we could call this force the strength. Why? Because we define the motion of the block, the incipient motion of the block, as failure. So the force that is producing that failure, in fact, the force during the failure condition, which is the incipient motion of the block, gets a special name, which is the strength. So the coefficient of friction is the relationship between the strength of the system and the normal force, in this case, acting on the interface. Now, this is the case of a solid block or an object on a plate, right? For soil, what we do is, as you know, one way to do this is to take a specimen, place it in a direct shear device where the bottom, let's say, is fixed, the top is free to move, right? We apply weights to the top of the specimen, and that weight divided by the cross-sectional area over which that weight acts is equal to the stress, normal stress, a sigma, right? Then we push the top with a machine, basically, and we monitor the deformation and the load imposed during the deformation, or the load that is sensed, let's say, by the rod that pushes this top part of the specimen. So this produces a failure surface that is horizontal, right, in the specimen. And then what we do, as you know, is plot the deformation versus T, the force that we measure. Now, the force that we measure is a shear force, right? Because it's a force that is parallel to the plane on which failure is occurring. If we divide that force by the area of this failure plane or failure surface, we get a shear stress, because this is a shear force, right? Shear stress acts here. So if we plot tau versus delta, we get, we may get a curve like that. This curve is associated with this sigma that we applied, which is equal to some value. We impose this sigma, okay? And then we say that this right here is the strength at the peak, and this right here is the critical state strength associated with this tapering, okay, or this flat portion here. Now, for the purposes of this class and continuing on, we're going to assume that this is the strength that we're going to use for design, for engineering. So you can ignore this strength. Okay, now, what do we want? Remember that this is analogous to this, right? So what we want, just like here, is the relationship between the strength, and the force, in this case, that is normal to the interface, in this case, the sigma that is normal to the interface. Here's the interface. Here's this interface. Okay? So, let's write it. Strength equals normal force times mu. Strength equals normal stress, right? Times mu. So, the relationship is this. Same as this. Strength over normal stress, strength over normal force, mu, mu. Okay? Now, few things. Remember, here, failure is the incipient motion of the block. Here, failure is what? It's a little bit more abstract, or appears to be. Why? Because this is always moving. So, you know, what's during the test, I mean. So, you know, here incipient motion, yes, but here, you know, what is it? Well, it's denoted here by the curve. As engineers, we've decided that this portion here, where increasing the deformation doesn't lead to any changes in resistance, this critical state region here, we're going to assign the stress associated with that, the shear stress, and we're going to assign that shear stress the term strength. Okay, so that's our definition of strength for this system, and our definition of strength for this one is just simply the incipient motion of the block. Now, if you wanted to know the relationship between the strength and the normal force for a block on a plate, what you would do is you would take a block. I'm repeating myself here, but I just want you to see this approach, which is the reverse approach. If you wanted the relationship, you would take a specific block, you know the weight, so you know N, and then you would push until this starts moving. The moment this starts moving, you know what force you are pushing with, and therefore you can say, I know what force I'm pushing with, or that I know what force I used so as to slide the block. I know the weight of the block, so simply this is the relationship. So I'm done. So if you were looking for the relationship, you would do this experiment. Here, if you're looking for the relationship between the strength and the normal stress, you would do this experiment. The thing is that in this case, the case of soil, the relationship is a little bit more complex. Why? Because soil, first, may exhibit bonding between the grains, and two, the relationship may vary with this stress here. Okay? These are the two main reasons. So I'm going to show you how to get the relationship using the direct shear test for soil, which is not specifically this, but it's an expansion, let's say, of this. So let's do it. Let me just turn this around. All right, so this is the equation we know so far. We're not going to use this equation particularly. We're going to expand it and you'll see why. This is actually, let's say, separated into two parameters. One is called phi, the other one is called C prime. The mu is actually more related to the phi prime rather than the C prime. But basically what I want to show you here is that for soil, the relationship is not mu. The relationship is described by two parameters. Okay, you'll see how this come about. How do we do this? Okay, one way, and this is the way we're going to learn in this class, is the direct shear test, right? That you know how to do. And you're going to do at least 3 tests. 3 tests. Now, what do you do? Well, test number 1. Take your sample, right? Place it in the direct shear device. Place a load that divided by the area is equal to a stress. And then you monitor delta. Well, you push this and monitor the force T, right? And of course what will happen is there will be a failure surface here and then you will plot. Now, important. When you apply a weight here, or impose a weight, who takes the load? Meaning in the soil, the water or the grains. Remember that this whole apparatus is submerged in water, so this soil is saturated. So if you place a load here, a weight for example, the water in the pores is going to carry the load first, and consolidation will then occur so as for the water to transfer the load to the grains, right? So there will be a little, generally there's a little settlement or deformation, axial deformation of the specimen, of course due to consolidation. Now the way these tests are done is as follows. You place the weight on top and then you wait. You wait until consolidation of the specimen ends. At that point, you know that the particles are carrying the weight that you applied. And therefore you can place a prime here to denote that. This is the effective stress, the stress that the particles carry. Once that is done, meaning once consolidation ends and you place a prime here, because you know the particles are carrying the load that you imposed, then you start the shearing stage, which means that you start pushing the top to create this failure surface and to plot this curve. Okay? That curve is for this effective stress. Let's say that this effective stress is, let me see, I have written some numbers over here. Yeah, let's say this effective stress is 15 kPa. Okay, so you impose 15 kPa for this test, test number 1, and this is the curve that you got. So then you can extract the strength, critical state, which is, let's say, 20 kPa. Okay? Number 2. Test 2. For test 2, you take another sample of the same exact soil, of course, because remember, you're trying to get the relationship between strength and stress for a specific soil. That is why we are doing all this. Okay? So, same thing, you apply a stress, you wait for consolidation to end, therefore you can place a prime here. You run a direct shear test, and let's say in this was 15, right? Let's say in this case this is 5, so lower, a lower stress. You impose a lower stress, you run the test, and you plot it in the same plot. In this case you may get something like this. Maybe a little peak or not even, maybe no peak. Okay, so this is for an effective stress of 5 kPa. Same soil, of course. Critical state strength in this case, let's say it's 15 kPa. Notice that S is a tau, of course. Alright, now number 3, test number 3. Same thing, right? Apply a stress, wait for consolidation to end. You can place now a prime here. Let's say in this case, it's, what did I write over here? 30 kPa. So let's say that you apply a stress of 30 kPa, then you run the direct shear test. And in this case, your curve will appear higher, like that. Okay, so, okay, sorry, I ran out of space. All right, so we were saying that we ran one test with 15 kPa, strength is 20. Another test with the same soil, right? Another sample, but exactly the same soil. We applied a stress of 5. We ran the test, and we got a strength of 15 kPa. And then the last one we ran with 30 kPa, and the strength we got was 25, let's say, kPa. So remember, we run this test to measure the strength for the stresses that we have applied on the specimens. Okay, now you may ask, well, why is it that a soil, you know, we put the same soil in the three tests, how come they have different strengths if they are the same exact soil? Well, of course you know that the difference is because this soil down here, which is plotted, the results for which are plotted here, right? The soil down here is loaded with 30 kPa before shearing, whereas this one is loaded with 5 kPa before shearing. So, let's put a little note up here. If you take a block that weighs very little, right? The normal stress here is low, normal force, let's say. So the force required to push the block is small because the block weighs very little. Now, if the block is made of lead or something and weighs a lot, then you're going to have to push with a big force to push it, to actually cause it to slide, even though the coefficient of friction may be the same for both cases. Okay? So in the case of soil, I like to use the example where if you're looking at this interface, for soil would be looking at that interface right here between soil and soil. Particles grinding against each other basically along this failure surface. So one way to do it or to think about it is to think, well, I would have to go, I can't because of the tripod that I have behind my hands, but that is the interface, right? These are particles. So if I press my knuckles together hard, that's a high effective stress between the grains, right? If I press together hard, it's going to be hard for me to cause shear, right? Whereas if I softly press the particles together, which implies a small effective stress, then it's very easy to shear. So the strength is low. See, if I press them together, strength is high. There's actually interlocking. But if I press them together softly, you know, it's easy to shear. So that's what happens. Basically, that's what happens in here. The grains grinding against each other, they're just like knuckles. At high stress, you have a high strength. Low stress, you have a low strength. So even though you have the same soil, you have different strengths, right? For different imposed stresses. Now, that is the first part of the procedure to determine the relationship. Remember the relationship between the strength and the stress imposed, which in this case we could put a prime here, right? Because we're talking about effective stress, stress that the particles feel, not the water. And that relationship is described as these two parameters, which we haven't figured out yet. We're going to do that now. So, you take the data and you extract the coordinates for points that you're going to plot in the Mohr circle space. Effective stress, tau. Instead of tau, what we can do is put a comma and say strength, because strength is a tau. So we're going to plot strength, the three strengths, versus the three effective stresses. Very simple. So, the Mohr circle space needs to be plotted perfectly. So I wish I had engineering paper, but I don't. In your case, you should always do this with a ruler or engineering paper. Okay, so not perfect, but you know, it's okay. At least for this lecture. So 5, 10, 15, 20, 25, 5, 10, 15, 20, 25. Okay? So, first one, effective stress 5, strength 15. 5, 15. That's test number 2. Okay? Next one. Stress effective 15, strength 20. So 15, 20. That's test number 1. And then the last one, effective stress 30, strength 25. Test 3. Okay, so we have 3 points in the Mohr circle space. Now, what we do to get the relationship is we look at the points and we realize that they fall for the, you know, for a rough approximation, basically, they fall on a straight line. So, look, if we apply a stress of 5, we'll get 15 as a strength, which we did, right? Of course, it's a point. If we apply a stress of 15, we get a strength of 20. If we apply a stress of 10, we may get a strength of about 17, right? So we are basically saying that the relationship between the stress and the strength is denoted by a line, which we as engineers decide to create by best fitting the points. This angle is phi prime. So this is an angle, okay? And this intercept here, this value, is called C prime. And C prime is a tau. It is a strength, actually, because it's on the strength envelope. Strength envelope. The strength envelope is the relationship between the stress, effective, that acts on a failure plane, and the stress, maximum stress that can be sustained there, which is the strength. Okay? So this line is the relationship. That's what we're looking for. And of course the relationship is described by phi prime and C prime. Why? What is the equation of a line? Y is equal to mx plus b, right? Let's write it in this case, for this line. What's y? Strength. What's m? The slope. Now for slope, what we can do is get this angle and take the tangent of it. X plus b. B is the intercept, so C prime. So generally for elegance, we put this sigma prime back here. So we say critical state is equal to sigma prime tangent phi prime plus C prime. Okay? That is the strength equation. That is the relationship between strength and effective stress. And it is, of course, it reflects two properties of the soil. This is a soil property and this is a soil property. The internal friction angle is a soil property. It's a property of this particular soil that you put in the three specimens, or you put in these three direct shear test devices. These are specimens of soil. Okay, and this is called the cohesion, like bonding, cohesion, right? Intercept. Why intercept? Because it's the intercept of the line, the b. Y is equal to mx plus b. Okay, so that's it. This is the relationship. When we run direct shear tests, or we want to determine the strength properties of a soil, strength parameters, we're looking for that one and that one. These are material dependent. Okay, they vary from soil to soil. Some soils have C prime equals 0. I'll tell you a little bit about this in a second. Okay, now well, let's discuss these two before we actually do an example where you will see how this is used. The internal friction angle is an angle, of course. The units are in degrees. Okay? And that tells you the relationship, again, the slope, right, which is a relationship between this and this. The effective stress and the strength. This one is part of the relationship because it's the intercept. So look, for 0 effective stress, the strength is C prime. So we're saying that if there's zero stress between my knuckles, there is still a strength. How can that be? I mean, if the knuckles are not touching, I ensure that there's zero stress between them, right? There's no resistance. So how come a soil can exhibit a strength called C prime when the effective stress is zero? It's actually very simple. Sometimes the grains are bonded, they're glued together. Okay, so we can take plastic, for example, or cement, Portland cement, and inject it into the soil, or resin, right? And cause the grains to bond. So if you have in here a soil where the grains are bonded, you're going to get, when you do all this stuff, you draw your line, you're going to get a C prime. C prime also emerges when the grains are bonded by electrical forces, or electrical agents, let's call them, okay? So you may get, definitely, of course, particularly for soils that are fine-grained, you may get a C prime. And that's part of the strength. That is the strength at zero stress. The C prime, the value, in this case is about 12 kPa, right? 5, 10, 15, so this is about 12 kPa for this soil. Okay? That is dependent on the strength of the bond. Okay? The strength of the material that makes the cement, or the bond between the grains. For example, you may have calcium carbonate, that's a natural cement agent that cements grains together. In that case, this value would reflect the strength of that calcium carbonate. Okay? All right. So, what else? Okay. So this is the relationship. This is what you want when you run the tests. You want phi prime and C prime for the soil. Now, let's say that you that you go to a meeting and you're talking about a soil from San Diego, and the person you're talking to asks you, tell me something. What is the strength of that soil that you're working with at your site or whatever, right? So let's say you have a site and you're going to construct a building, right? And somebody asks you, what's the strength of the soil here, of your soil at the site? Well, if you think of the equation, you would say, okay, well, the strength, you wouldn't really be able to answer that question because the strength of the soil depends on the effective stress. So what you may say is, look, I don't know what you're referring to with this question, but I can tell you that my soil, which is a silty sand, has a phi prime of 40 degrees and a C prime of 20 kPa. Okay? So that's my answer. Now the person may say, well, but what's the strength? And you have to say, your answer should be, well, I can't tell you the strength, because to tell you the strength, you would have to tell me what point and on what plane, for example, the horizontal plane, you want me to calculate the strength based on these parameters. Okay? So generally, when geotechnical engineers refer to strength in an informal way, when they ask each other, for example, hey, what's the strength of your soil? What they're asking is, what's the phi prime and the C prime of your soil? Okay? They're not asking what is the strength. There's another type of strength which is called the undrained strength, and that is one single value, and we'll get to that in a second. But in general, when people ask for strength, they're asking for phi prime and C prime, particularly phi prime, because this is the one that actually tells you the relationship, the strength over the phi prime, right? Or the sigma prime. This one is the intercept. Anyway, so let's do a little example here. Let's say that you have a site. This is a point. The point is 5 meters. Underground is a water table, and gamma is 20. Okay, and you want to know this. And sorry, the phi of this soil is 40, and the C prime is, let's say, like over there, 20 kPa. So you want to know the strength, critical state strength of the soil at point A on the vertical plane. Point A on the vertical plane. Let's do it like that, okay? We need a K value, 0.5, let's say. So then you say, okay, I want the strength. I know the strength equation, right? So let's fill it out. I know tangent 40 plus 20 kPa. Now, effective stress. What is the effective stress that I have to put here? Well, very simple. It is the effective stress that is normal to the plane on which you want the strength. So what is the effective stress acting on this plane at this point? Well, that effective stress is equal to 5 times 20, right? 5 times 20, that is the vertical stress, times K, 0.5. So this is 100 times 0.5 is 50. So then, put the 50 here. The strength is 50 times tangent 40 plus 20. That is the strength at point A on this plane. What about the strength at point A on this plane? Well, on this plane, the stress acting on the plane normal to it is the vertical effective stress, which is 100. So the strength at point A on this plane is 100, which is that stress, normal to the plane, times tangent of 40 plus 20. So the strength on this plane is larger than on this plane. The strength on this plane is larger than on this plane because the stress on this plane is larger than on that plane. The phi and the C are the same. It's the same soil. Silty sand, let's say. Okay? Same soil everywhere. But the difference is the effective stress. Okay? Now, what happens if you want the strength at this point, but on this plane, which is oriented 31 degrees from the horizontal? Well, same thing. Strength, sigma prime, tangent phi plus C prime. Phi prime is 40 degrees. C prime is 20 kPa. The effective stress is now the one that acts on this plane like that, normal to the plane. See that? How do you get that stress? You have to draw the Mohr circle and do all your procedure that you have to do, basically, to get the stress that acts on this plane. So, draw your Mohr, you know your principal stresses, but the vertical and horizontal one in this case, tau sigma prime, right? You draw your element, you rotate it. This means that you would have to rotate this line 62 degrees. And this effective stress right here is the one that you would put here. Okay? Or here basically. That effective stress times tangent 40 plus C prime, which is 20, is equal to the strength at this point on this plane. Okay? Now, Mohr circle, that procedure, you already know how to do it. That is the reason that is the reason why you were asked before to learn how to determine the effective stress on any plane, not just the horizontal and vertical planes, but any plane, so that you can later get the strength of the soil at any point on any plane, provided that you have C prime and phi prime. Okay? One last thing before we get to the on-drain strength. Some students make the mistake of thinking that this 31 degrees is the one that needs to be put here for phi. And that's completely wrong. Why? This 31 degrees, or this angle, is the angle of the orientation of a specific plane that in this case the professor wants you to get the strength for. Okay? So this is just a random angle for an orientation of a plane along a point. This phi, which is 40 degrees, provided here, which is the one that you determine when you run tests in the lab, is a material property. And it's kind of weird, yes, to assign a material property with an angle. You know, what is the strength of your soil? 40 degrees. That sounds weird because it's an angle. How can strength or a strength parameter have units of degrees? Okay? The reason is because the tangent of this angle is the slope of the relationship between the effective stress and the strength. So this is a material property. That depends on the soil and on the soil density and on the shape of the grains and on the grain size distribution, etc. This angle is just, in this case, my selection of the orientation of a plane that I drew randomly to show you how you would have to use the Mohr circle to actually get the strength at this point on this plane. Okay, so don't confuse an angle that is provided by the problem with a material property, which is in this case 40 degrees for phi. Phi is the material property, phi prime.